Welcome to This Explainer. Today, we're engaging in a highly focused, data-driven examination of what is, without a doubt, a pivotal shift in renewable infrastructure. The thesis we'll be exploring is clear. Floating solar is India's next massive clean energy frontier. By transforming existing aquatic infrastructure into power-generating assets, we're literally looking at a fundamental redesign of how densely populated nations scale up their renewable capacity. So, let's dive right into this. I want you to consider a fundamental question. Why exactly is floating solar India's next energy breakthrough? We already know India has expanded its solar capacity over 50-fold in the last decade, reaching well over 162 gigawatts. But as land becomes increasingly scarce and, frankly, much more expensive, how does a nation continue that exponential growth? That geographic bottleneck is the central analytical focus of our explainer today. While the answer to that geographic bottleneck lies in a definitive policy catalyst. The government of India recently approved the Pradhan Mantri Surya Sarovar Yojana. This is the precise mechanism designed to take this emerging technology and upgrade it into a mainstream energy solution. It deliberately targets the conversion of existing water surfaces, think reservoirs and industrial ponds, into clean energy assets. This entirely sidesteps land acquisition conflicts while simultaneously enhancing the reliability of our electrical grid. To make sure we cover all of this comprehensively, here's our roadmap for today. We'll start with the floating solar breakthrough, then move to decoding floating PV systems, outline the PM Surya Sarovar Yojana, cover the strategic advantages, critically examine engineering and ecological hurdles, and wrap up with the path forward. Okay, Section 2, Decoding Floating PV Systems. Let's establish a strict baseline, so we're all operating from the exact same understanding. Floating solar photovoltaic, or FSPV systems, are essentially your standard solar panels, but rather than being ground-mounted, they're secured onto specialized floating platforms or pontoons. We deploy these strategically on inland artificial water surfaces, specifically targeting reservoirs, canals, and industrial ponds. And the sheer scale of this opportunity? It's staggering. We are looking at 102.18 gigawatt peak. That's the official assessment from the National Institute of Solar Energy, and it represents the cumulative floating solar potential across India's suitable inland water bodies. To put that into perspective, capturing even a fraction of this potential could radically alter the energy matrix of the entire country. Geographically speaking, this potential is highly concentrated. If we look at the top 5 states, Maharashtra, Madhya Pradesh, Karnataka, Odisha, and Telangana, they collectively account for nearly 68.4 gigawatt peak of the nation's total potential. For states dealing with high agricultural intensity and dense populations, this represents a massive, untapped reserve of clean power that simply doesn't compete with farming or human habitation. Moving on to Section 3, PM Surya Sarovar Yojana. Let's systematically break down the core parameters of this scheme. It targets 5,000 megawatts of new capacity. But crucially, it mandates the co-location of a minimum 2-hour energy storage system, totaling 10,000 megawatt hours. This specific storage requirement is a real masterstroke for peak demand management, making the power dispatchable precisely when it's needed most. Backed by an outlay of 5,070 crore rupees over 5 years, it provides up to 1 crore rupees per megawatt in central financial assistance. Plus, it includes vital funding, an additional 50 lakh per project specifically for de-risking preparatory activities, like environmental studies and bathymetry, which is the mapping of underwater topography. To truly grasp the significance of this policy, think about the traditional approach. Traditional utility-scale solar parks require vast, sprawling tracts of land. That inevitably leads to complex acquisition processes, long clearance delays, and severe friction over agricultural or forest land use. In stark contrast, floating solar PV elegantly solves these geographic bottlenecks. By utilizing existing water surfaces, it creates a secondary economic use for infrastructure like dams, without displacing their primary, vital function of storing water. That brings us to Section 4, the strategic advantages. Beyond just resolving those land constraints, there is a fascinating symbiotic engineering relationship at play here. The water actually physically cools the operating temperature of the solar panels above it. And because photovoltaic conversion efficiency drops as panels get hotter, this water-induced cooling effect actually boosts their electrical output compared to standard ground-mounted systems. Furthermore, being positioned out over water significantly reduces dust deposition. That means lower soiling losses and much less water required to constantly clean them. And the benefits are deeply reciprocal. The panels shade the water, which directly cuts down on evaporation losses. In water-stressed regions, conserving this volume is absolutely critical. It actively supports local drinking and irrigation requirements. This brilliantly illustrates how the technology creates a combined water and energy asset, drastically enhancing a region's overall resource security while smartly piggybacking on existing dam and transmission infrastructure. Zooming out to the macro level, the strategic impacts are profound. Remember that mandated energy storage? It allows grid operators to shift cheap daytime solar generation to offset really expensive peak-hour thermal generation. Environmentally, the scheme is projected to abate approximately 10 million tons of CO2 emissions every single year. Economically, we're looking at generating 16,000 to 17,000 full-time equivalent jobs, which drives a highly specialized domestic manufacturing value chain for pontoons, mooring systems, and batteries. This perfectly aligns with India's broader national target of 500 gigawatts of non-fossil electricity capacity by 2030. Now, let's turn to Section 5, Engineering and Ecological Hurdles. As focused learners, our job isn't just to cheer for the upside, we have to impartially assess the limitations. The capital costs are initially higher because you need specialized cables and specialized floating structures, but the most severe engineering hurdle is hydrodynamic stability. Reservoirs experience massive water level fluctuations between the monsoon and dry seasons. Designing anchoring and mooring systems that can maintain optimal tension across these massive depth changes is vastly more complex than just pounding steel into dirt. Add to that the constant exposure to extreme weather, like high winds and storms, and the structural risks become very significant. Furthermore, the operating environment itself is just inherently hostile to electrical equipment. Persistent moisture introduces unique and severe degradation risks. We are looking at rapid corrosion of metallic components, electrical faults driven by constant high humidity, and biofouling, which is where algae and aquatic organisms physically grow on the floats and the mooring lines. All these factors heavily drive up long-term maintenance and operational expenditures. Then, you have the ecological and social friction points. Scientifically, covering a large percentage of a water body restricts the interface between sunlight and air, which can potentially alter dissolved oxygen levels and temperature profiles, which can seriously stress local aquatic life. Socially, these giant installations might conflict with local fisheries or navigation routes. Finally, there's a hard infrastructural reality. A lot of these prime reservoirs are remote, meaning they lack the high-capacity grid transmission lines necessary to actually evacuate the generated power. Which brings us to our final segment, Section 6, the path forward. To successfully mainstream this technology, 4 non-negotiable scientific prerequisites simply must be met. First, before any deployment, strict reservoir-specific bathymetric and environmental assessments are mandatory. Second, we must establish rigorous limits on the percentage of surface area covered, limits dictated entirely by the specific ecological carrying capacity of that particular water body. Third, the industry urgently needs standardized national technical codes for hydrodynamic anchoring and safety. And fourth, project life cycles must include continuous, real-time monitoring of dissolved oxygen, temperature, and local biodiversity. Beyond the hard science, holistic success absolutely requires socioeconomic integration. We have to prioritize reservoirs that already possess nearby transmission infrastructure to help control those capital costs. Crucially, planning must actively involve dam authorities and local communities from day one to protect existing fisheries and livelihood access. Furthermore, for this to be truly sustainable long-term, we must promote domestic manufacturing of corrosion-resistant equipment and implement strict circular economy protocols for the end-of-life recycling of these specialized panels, batteries, and high-density plastics. And that brings us to the ultimate takeaway. We've examined the data, the policies, the immense benefits, and the severe engineering realities of the PM Surya Sarovar Yojana. As we look ahead, I want to leave you with this final provocative thought. How exactly will the dual use of our vital water infrastructure reshape the clean energy landscape in your own state? Are your local reservoirs destined to become the power plants of tomorrow? Keep that in mind as we watch this technological breakthrough transition from a blueprint to reality all across the country.